morning. Let's proceed with our discussion on the logical effort. Okay. NAND 2. A, B, A and B. Right. Then size is 2, 2, 2 and 2. So what's the net capacitance on input A? It is sum of both NMOS and PMOS capacitance. Right. So therefore you will get 4C. 2C from here and 2C from here. Right, and logical effort is defined as the ratio of input gate capacitance to the gate capacitance of a static CMOS inverter with identical drive strength. Okay, so because we have sized the NAND gate already to have 2, 2, 2, 2, wherein we have made sure that the resistances are the same already, our reference inverter here is just going to be the standard reference CMOS inverter, which is going to be 1, 2. So this capacitance will be 3C. So the logical effort will be how much? 4 by 3. What about the parasitic effort or the parasitic delay? Right? If you look at the output capacitance here, diffusion capacitance, it is 6C and here it is 3C, right. Therefore, P is going to be 6C by 3C, that is equal to 2. Logical effort we denote by G, parasitic effort we are going to denote by P, right. The parasitic delay we also, normalized parasitic delay we also call parasitic effort, P. Okay. This is logical effort and this is okay. So similarly, let's do one more for the NOR 2. A, B, A and B, this is VDD. Sizes are 1, 1, 4, 4. What's the net output cap? Again 6C. 4 coming from here, 1 coming from each of these. 6C is the output cap. Capacitance CA equal to CB equals how much? 5C. 4 coming from PMOS, 1 coming from the NMOS. So net capacitance is, so logical effort G, actually remember logical effort can be different for different inputs. In these cases they just happen to be the same. GB equals how much? 5C divided by 3C, that is 5 by 3. And parasitic effort is obviously not dependent on the input, it's only the output diffusion capacitance that we are counting, right. P is going to be 6C divided by 3C, you get a parasitic delay effort of 2. Okay. So what is the logical effort for an n input NAND gate and an n input NOR gate? Can you calculate that now? Why? Same as what? Is that so? So if you take a NAND, you have NMOS transistors on the stack. Size is N, 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 and PMOS is all 2. Like that you go. Y. So the net capacitance here is how much? 3N. 3N into C, right? 2C coming from each of the N PMOSes and NC coming from the top NMOS. So you get 3NC. And what's the input capacitance? CAK. So this is A1, or A1, A2, AN. A1, A2, AN is N plus 2 into C. Therefore, logical effort on each input is N plus 2 into C divided by 3C. Because I have to now compare this to a reference inverter with size 1, 2. That's how we have sized the. Later you will see that I can actually do different sizing for the NMOS and PMOS, in which case the comparison with the reference inverter will be different, right? That will be a different inverter and therefore you will get a different logical effort. Okay? Anyway, so you get now the answer as N plus 2 divided by 3. Okay? What about the NOR? So this is size 1, 1, 1. By the way, what is the parasitic effort here on the NAND? It is 3NC divided by 3C, which is equal to N. Okay? Now what is the input capacitance on each input? A1, A2, AN. A1, A2 and AN. So what is the PMOS size, by the way? Huh? 2N. 2N. So what is the net capacitance? Huh? 2N plus 1 into C. 2N coming from PMOS, 1 coming from NMOS. Therefore, the logical effort GAK is how much? 2N plus 1 into C by 3C. That is equal to 2N plus 1 divided by 3. What about the parasitic effort? You get 2N coming from the PMOS and NC coming from the NMOSes. So you get again 3NC, right? So this is 3NC divided by 3C equals back to N. So again, if you look at this, the logical effort, as I increase the stack, be it NMOS or PMOS, is going to increase, right? So apart from the fact that your parasitic delay went as square of n, earlier you remember we did this derivation, the parasitic delay goes as n square. So putting these two reasons together, it's obvious that you don't want to have a very large stack. The moment you have a large stack, your logical effort will go up, your parasitic delay will start going up significantly. Okay? This, of course, this approximation doesn't hold there, counting just the output diffusion capacitance. You have to calculate the actual Elmore delay, right? This approximation is also assuming that the stack is not very large. Okay? So therefore, don't make transistors with more than 4, don't make logic gates with more than 4 transistors on either stack. Clearly, it is much worse to stack transistors on the PMOS rather than on the NMOS, because the logical effort is now going up as 2n plus 1 by 3. Again, what does this logical effort mean? It means that in order to achieve the same resistance, I need to pay a higher price in the input capacitance. This 2n plus 1 by 3 compared to n plus 2 by 3 of the NANDs tells me that I need to pay a higher price on the input capacitance for NORs compared to NANDs in order to achieve the same resistance, right? And thereby the similar delay of charging a load capacitance. So let's just get back to our delay that we talked about yesterday. Okay, we said that we had, let's say, some device under test and it was driving a load capacitance CL and its capacitance was C DUT, right? That is the gate capacitance that it will present after upsizing and all that, not the unit gate's capacitance, what the gate actually presents in the circuit. So this we said we could write as CL by C DUT into C unit by C inverter, right, plus the parasitic delay P. We define this to be the logical effort G, and this, as I told you yesterday, is nothing but the electrical effort H, right? So this is parasitic effort, this is logical effort, and this is called electrical effort. The electrical effort depends on the drive strength of the gate. If I have a 1x gate, then it presents less capacitance. If I have a 10x gate, gate has been upsized by a factor of 10, then it presents a larger capacitance and therefore the electrical effort will change. Okay? So this is the guy that actually captures the sizing part of the gate. The G only captures the logical part. Whatever logic function it is implementing, it captures in some abstract form that complexity, right? A trade-off between resistance and capacitance it captures. Now the presence of the actual capacitance in the circuit because of upsizing that gate is captured by the electrical effort E, and therefore the normalized delay, I'll call it D hat, can be written as GH plus P. Okay, and how do you get the absolute delay from this? You just have to multiply it by the delay of the reference inverter that we divided by. So let me call the reference inverter delay as tau. This was 3 RC, right, under no load condition. Inverter driving no load, then the delay was 3 RC. So if you want to get the actual delay, you multiply the normalized delay by tau. Normalized delay. Okay? So what is this saying? If I plot my normalized delay as a function of the electrical effort H, I will get a straight line with some offset on the y-axis, right? So if I take a NAND gate, it would be something like this. For an inverter, right, obviously it is simply going to, G is 1 by definition, P is also 1, right? So the slope will be the best for an inverter, right? And this is for a NAND where the delay starts at 2, because the parasitic delay itself is 2, right? Even if you put no load, you will get that. Now for an inverter, it would be something like this. Lower slope, this is an inverter, this is a NAND 2. The slope is G equals 4 by 3, logical effort. A NOR 2 would have the same parasitic delay, so it would start at the same point, but the slope will be what? 5 by 3. So you will have NOR 2 G equals 5 by 3. Okay, so let us look at this thing. So if I have an inverter driving 4 copies of itself, you remember this we called as fan out of 4 delay, right? Because there are 4, the output is fanning out into 4 different gates and it is driving identical copies of itself. That's what we mean by fan out of 4. So what is the net load capacitance on this load capacitance? CL. Huh? Sorry? No, only load capacitance, not parasitic capacitance. Yeah, 4 times. So let us assume that this guy is presenting a capacitance of 3C. Okay? So what is CL equal to then? Huh? 12C. Right? Because all are identical inverters. Therefore, my H is going to be what? Output capacitance, C load divided by C input. Whatever input capacitance you are going to see here. This is C in. And that is 3C. So you can write this as 12C by 3C equals 4. So therefore, FO4 delay is GH plus P into tau, the actual delay. So this I can write as 1 into 4 plus 1 into tau equals 5 tau. Just 5 tau. Okay. Now you think about this. Suppose this inverter were not the unit inverter and instead I upsized everything by a factor of k. Everything. The whole thing went up by a factor of k. Then what would happen? All capacitances would go up by a factor of k. Correct? That's the only thing that is going to affect the delay is H, because of the gate sizing, right? Other things are just constant irrespective of the gate size. So if you write this, you will find that this also goes up, right? The H will be 12 kc by 3 kc, that's again equal to 4. So it doesn't matter when you're, if I tell you fan out of 4 delay in a technology, it doesn't matter what the size of the inverter was. You understand, the fan out of 4 delay is the same whether you did it for a unit inverter or for an upsized inverter or for an inverter with higher drive strength, because the delay comes out to be the same. The H is effectively the same because I am scaling up all capacitances by the same factor. So if I tell you in a technology the fan out of 4 delay is some 100 picoseconds, then you don't have to ask any further questions. You know that therefore the inverter delay is just 1/5 of that. Clear? So this FO4 delay is an important characterization that people will do in VLSI. When you go to a new technology, first thing they will characterize is what is the FO4 delay of the inverter. Okay? Just a thumb rule, this FO4 delay, if you are in a technology 180 nanometer, then the FO4 delay is typically between half and 1/3 of that technology node in picoseconds. If you are in 180 nanometer, half of that is 90, 1/3 is 60. So the FO4 delay will typically be between 60 to 90 picoseconds. Okay, and then you can calculate what the inverter delay is, which is just 1/5 of the FO4 delay. Okay.